Welcome back to The Explainer. If you're a focused learner trying to wrap your head around the mechanics of our connected world, you're in the right spot. Today, we're taking on a massive, complex topic and breaking it down into crystal clear steps. We're going to completely untangle the often chaotic world of fog computing by looking at the true masterminds behind the curtain, software-defined networking, or SDN, and the OpenFlow protocol. Get ready because we're about to see exactly how centralized intelligence brings order to millions of decentralized devices.
Okay, let's jump right in. To really grasp the problem we're solving today, I want you to imagine a completely chaotic city intersection. You've got 50 individual traffic lights, and every single one of them is operating on an independent, uncoordinated timer. They only make decisions based on the cars directly in front of them. So if an ambulance is racing toward them from 5 miles away, that local traffic light has absolutely no idea until the ambulance is physically right there. The result? Cars crashing and massive traffic backups. Honestly, this is exactly how traditional computer networks operate. Every single router is an independent brain calculating its own paths. But now imagine a different scenario, a central smart city control room. One AI monitors the entire grid simultaneously, dynamically changing the lights to create a perfectly timed path for that ambulance. That right there, that's the exact shift we're talking about today.
Here is our roadmap for today. We'll start with the traffic light problem, move into the SDN architecture, crack open the OpenFlow protocol, look at network slicing realities, and wrap up with key takeaways. Let's get into it.
Section 1. The traffic light problem, navigating traditional network chaos.
So when you're dealing with massive fog computing environments, literally thousands of edge nodes scattered everywhere in the real world, trying to update policies across all those independent, uncoordinated devices is just a complete nightmare. Enter software-defined networking, or SDN. Think of SDN as the hero of our story. It acts as that centralized command center, the smart city AI viewing the entire network at once to orchestrate those clear paths. It's the very mechanism that injects centralized intelligence into a highly decentralized system.
Section 2. The SDN architecture, decoupling the brain from the muscle.
In a traditional setup, every single router is basically a tightly coupled two-in-one package. First, you've got the control plane. That's the brain. It makes the complex routing decisions using protocols like OSPF or BGP to figure out exactly where traffic should go. And then you have the data plane, which is the muscle. It doesn't think at all, it literally just shoves packets out the correct port based on what the brain told it to do. When these two are permanently glued together inside thousands of different routers across a network, making any kind of system-wide update is totally exhausting.
But SDN? It completely flips the script by physically decoupling them. It takes a metaphorical sword and just slices that traditional router right in half.
By slicing things up, we get this really elegant three-tier architecture. Starting at the bottom layer, we have the data plane. Because we remove the brains, these are now essentially just dumb forwarding switches. They don't calculate a thing, they just follow strict instructions. Right above them, in the middle, sits the control plane. This is our SDN controller, the new centralized software brain with a god's eye view of the entire network. And finally, sitting at the very top is the application plane. This is where network admins actually write the software programs to manage traffic, security, and load balancing for the whole shebang.
Now, these layers can't just exist in a vacuum. They have to talk to each other, and they do that through APIs. The connection between the top-level applications and the middle control plane is called the northbound interface. Going the other way, the protocol connecting that middle control plane down to the dumb switches in the data plane is called the southbound interface. And in the networking world, there's really one undisputed king of the southbound interface.
Section 3. Inside the OpenFlow protocol, the undisputed king of southbound interfaces.
To let that central SDN controller reach down and directly boss around those switches, we use an open standard called OpenFlow. The absolute secret sauce inside every OpenFlow switch is a flow table. You can think of a flow table as a highly specific conditional instruction manual. Every single entry in there has 3 core components. First up, match fields, basically asking, what does this incoming packet look like? Second, counters. These keep a running tally of stats, like how many packets match this rule, which is super handy for billing or load balancing. And third, actions, meaning what on earth should the switch actually do with this packet?
In the real world, the process goes a bit like this. A switch checks the match fields to see, for instance, if an HTTP packet is coming from a specific IP address like 192.168.1.5. Then it hits the counters to log the active time and byte count. Finally, the actions kick in. The switch might forward the packet to a specific port, just drop it entirely, modify the header, or, if it's totally clueless, punt it up to the controller. And all of this evaluation happens at blistering wire speed, thanks to specialized memory hardware known as TCAM.
But what happens when a switch gets a packet that just doesn't match any of its rules? Well, here is the exact flowchart. Step 1. The dumb switch receives the unknown packet and gets confused. Step 2. It wraps that packet up in what's called an OpenFlow packet in message and fires it straight up to the central controller. Step 3. The controller looks at its global map and calculates the absolute optimal route across the network. Step 4. It shoots a flow mod message back down, permanently updating the switch's flow table. From that millisecond forward, the switch knows exactly what to do with those packets. No questions asked.
This level of dynamic control is honestly amazing, but it brings up a really wild real-world scenario. How do an autonomous car and a tiny smart agricultural soil sensor share the exact same physical network? If they hit the same cell tower and you treat their data equally, you are asking for disaster. The car needs instantaneous, life-saving reaction times, while the soil sensor is just casually sipping battery to send a tiny ping once an hour.
Section 4. Network Slicing Realities, Splitting the Multi-Lane Highway. To solve the soil sensor versus autonomous car problem, we have to magically split our network highway. We do this through network slicing. By leveraging SDN, we can take one physical network infrastructure and partition it into completely isolated, totally customized virtual networks. It's like taking a normal highway and instantly turning one lane into a bullet train track, another into a dirt road, and a third into a protected bike lane. The coolest part? Because our control plane is just software, we are doing the slicing logically in milliseconds, not physically digging up roads.
In modern 5G and FOG setups, these slices usually fall into three main buckets. First, URLLC, or Ultra-Reliable Low-Latency Communications. The SDN controller ensures this traffic is processed immediately at the edge. This is the life-or-death stuff: remote robotic surgery, self-driving cars. Next up is EMBB, Enhanced Mobile Broadband. Latency isn't fatal here, but the data volume is massive, so think 4K video streams and VR headsets. Lastly, MMTC, Massive Machine-Type Communications. This slice is built to handle millions of tiny simultaneous connections all at once. It's absolutely perfect for our little soil sensors.
Section 5. Key Takeaways, Acing the Exam and Beyond.
If you remember absolutely nothing else from this explainer today, please lock these three things in. Number 1. SDN physically decouples the control plane brain from the data plane muscle, bringing central smarts to decentralized edges. Number 2. OpenFlow lets that central controller program those dumb switches using match, counter, and action rules inside the flow tables. And number 3. Network slicing uses this exact software-defined architecture to build isolated, custom virtual networks right on top of the shared physical hardware.
So you've got a solid grip on how the network itself is structured and routed. Next time, we're taking the next logical step in our journey and diving into fog resource management. To see exactly how computing tasks get scheduled using the min-min and max-min algorithms, you definitely won't want to miss that. But before we wrap, chew on this for a second. Look around at all the smart devices you own right now. What does centralized intelligence really mean for the future of your own connected tech? As we push more computing out to the edge, the way these devices communicate is fundamentally shifting from total chaos to extreme orchestration. Keep reviewing these concepts. Trace that packet flow in your mind, and you'll have this totally mastered. Thanks for hanging out, stay curious, and I'll catch you in the next explainer.